So welcome everyone back to another GSI seminar. We have another really interesting talk for everybody, and it's one I'm particularly excited about. So today we have Dr. Tian as our speaker. She is actually a lecturer here in low carbon engineering at the University of Exeter. So her research focuses on understanding the structure property relationships of functional composites and their application to sustainable energies. And she has been leading the research on neuron scattering techniques for hydrogen energy materials, which provide fundamental properties for hydrogen and hence novel hydrogen material design, if I've got that correct. So she recently, well in 2019, received the Ede Ravencroft Prize and has also been recognised as one of the top 50 women in engineering in 2020. So we're really lucky to have her here sharing some of her expertise with us today. So I'm going to hand over to Mai, and she can show us how we can engineer our way to a low carbon future.
Okay, thank you, Amy, for such an introduction. Hello, everyone. Thanks for having me this afternoon. As mentioned, I'm Tian, a lecturer in low carbon engineering, and also I'm a first Global System Institute appointment in engineering. And just for some context, I completed my PhD on hydrogen storage and carbon capture at the University of East Anglia, and then worked on porous composite for onboard hydrogen system at the University of Bath before taking my current position. And today I'm going to give an introduction on the development of hydrogen energy and give an overview of my research projects related to today's topic. So I'm going to start out giving a brief background of hydrogen energy, why hydrogen matters, and then I'm going to talk about one of the biggest challenges in using hydrogen storage. Finally, I'm focusing on two of my research projects. Let's first take a look at how we use energy over a long term. If we look at this graph, the left-hand figure, the global energy consumption has increased dramatically. If we take a closer look, so since 2000, the total increase in energy consumption is about 70% to 80% within 20 years. And by 2019, so you can see this world energy consumption chart. Only 13% energy was provided by renewable energy sources, wind, solar, hydropower, etc. And the major proportion of energy we use are based on fossil fuel, carbon-based energy sources, which results in the increase of carbon emission. So it's pretty clear to me where we are headed. So population growth demands for energy rises, therefore CO2 emission rises, causing global warming. Scientists agreed that a temperature rise of more than 2 degrees would have an unprecedented impact on our lives. So to help us stay within that 2 Celsius temperature limit, carbon emission need to be reduced to 0 by 2050. It's astounding, but one of the pleasing is how quickly that language of net zero has got into our vocabulary. I meet people all the time who talk about net zero, which a year ago just wouldn't have been the case. So 80 countries now have committed to net zero by 2050. And of course, the UK, as the first country passed net zero emissions law, moves really quickly. And quite clear, the government gives a huge amount of attention on it. If we stand back and think about what net zero really means, it means that all man-made greenhouse gas emissions must be removed from atmosphere through reduction measures. So it's not 80% reduction anymore. Everyone involves. There's no hiding place. So which means we absolutely need to use all technologies, especially hydrogen. So the role of hydrogen in this decarbonizing process and the net zero commitment has been changed from an option to a necessity. So every effort, every trick needs to be made to reduce greenhouse gas emission in all sectors. If we take a look at UK's emission divided by sector, this chart, so since 1990, the UK has achieved steep emissions reduction in the energy supply sector, the pink curve. That is a result of phasing out coal and increasing the use of renewables, such as wind and solar. But in other areas, such as transport, home, emissions remain largely unchanged. So decarbonizing these areas is the main challenge, which is where hydrogen will contribute to. So how hydrogen works? Hydrogen can be produced from water using renewable energy sources, solar energy and wind power via electrolysis. So the idea is you bring your water and you can split your water into hydrogen and oxygen. And then you can use hydrogen to power your car, your house, and whatever needs energy to drive. Then afterwards, hydrogen will be converted into water again. So you can see this is almost a clean cycle. Water comes in and out. Hydrogen has a great potential to be amazing. But there's a lot of challenges in all three parts: hydrogen production, the use of hydrogen, and the hydrogen storage and transportation. So I'm coming back to storage and these challenges in a minute. So now I'd like to look at the hydrogen from this sustainability angle, particularly because I'm delivering the talk within GSI community. I think it's quite important to think about sustainability, although we don't usually talk about hydrogen. Actually, when we talk about renewables, because it is often goes with some kind of assumption that new clean technologies are automatically sustainable or green, and that isn't actually always the case. So I just want to draw some attention to parts of the hydrogen system really do meet some good sustainability criteria. One of the good things about hydrogen is that it can be produced in the UK using a low carbon electricity. So you can create a system here where you really don't need too much input from anywhere else. We got wind, water, and all of things that for hydrogen energy system. So it can be produced using waste. So again, it allows us to look at the different parts of our waste production and how we can use those to ensure that we are being as resource efficiently as possible. Hydrogen uses infinitely recyclable materials like platinum in fuel cells. This is a non-ferrous metal that can be recycled forever. There are a lot of other technologies that don't have that option. It allows us to reduce the use of non-recyclable materials and reduce the environmental damage that potentially goes with the extraction of those materials. And so it enables greater use of renewables through longer-term storage. At the moment, it is looking like it's really one of the only good storage options for making sure that we maximize the use of our renewables. And it enables better air quality through zero-emission vehicles. This is the area that the UK government pushes quite hard because there is a real opportunity to decarbonize much more quickly using alternative fuels than use battery electric vehicles, particularly for larger vehicles, heavy-duty vehicles. And it can become an export for the UK. And this is the area, I think, the most important area. Not only benefits the economy, but also reduce reliance on overseas imports, especially considering 60% to 80% of UK's energy imported abroad. But transport and storage of hydrogen is not the easiest thing. So as mentioned, hydrogen is a lightweighted gas and it's invisible, it's flammable. So storage and transport is extremely difficult and cost a lot of energy. So just to show you the problem of the hydrogen, and if we look at this figure, energy density figure, volumetric density against the gravimetric density. So hydrogen is at the bottom right. So if we look at the gravimetric density, that is energy per weight. So we can see hydrogen is twice higher than diesel or petrol. But if we look at volume density, so energy per volume, hydrogen is nearly zero. It's at the bottom. So which means a huge volume of hydrogen gas need to be used to generate the same energy as diesel or petrol, for example. So currently, we store hydrogen either in high pressure hydrogen storage tank at 700 atmospheric pressure, or liquefy hydrogen at a cryogenic temperature. And if you look at the left photo, that is hydrogen bus running in London, and we can see there are a huge 4 hydrogen storage tank sitting on top of the bus. And comparing with the size of the private car, you can see directly where the problem is. And both technologies also are energy intensive per size and also pose the serious risk issues. So my research is to solve this hydrogen storage and transportation problem. So we want to solidify hydrogen or store hydrogen in solid phase. A solid hydrogen not only solves the storage problem, but also has been predicted to be a near room temperature superconductor. Hydrogen phase can be changed by changing temperature or pressure. So this is a bit difficult to understand for hydrogen, but if you think about water, that is an easy example. So if we heat up the water to 100 degrees C in the air, so it turns to gas, water, steam. And if we cool down water into 0 Celsius, and we got solid water ice, similar to this, and hydrogen also can be solidified, liquefied by changing temperature or pressure, but the hydrogen boiling point and the freezing point are much, much lower. For example, solid hydrogen temperature is below 14 Kelvin. Oh, we need to pressurize hydrogen to 400 gigapascal. Is kind of extreme conditions, and these extreme conditions are very difficult and expensive to achieve and maintain. And I found the nanoporous materials has the ability to stabilize, to freeze hydrogen molecules at a relatively higher temperature, making it more practical to use. So the porous materials has a very special feature. They offer a large surface area and tiny pores. So the pore size of the material I'm working with the pore size is a million times smaller than humans' hair. So as soon as we expose the clean porous surface to ice, it will absorb, compress, and store hydrogen molecules in its tiny space. And we call this nanoporous material as a molecular sponge. So like a sponge absorbs water, so the molecular sponge absorbs gas molecules, and it can really compress hydrogen molecules to a very high density, without which we wouldn't achieve otherwise. So my job is to gain better understanding on how gas molecules interact with porous surface, therefore leading to a better design for the porous materials. So one of the challenges here is how to characterize this, how to characterize hydrogen inside the pores. As we just mentioned, hydrogen is lightweighted, it's invisible, and is inactive to the lab-based technology. So it's a challenge for hydrogen characterization. And neutron is the best candidate for this job. Neutron is highly sensitive to hydrogen, and the neutron beam can deeply penetrate everything. So that's why it's also dangerous. So this is the, just bring the laser pointer. So this is the neutron facilities located in Oxfordshire. So you can see this is a neutron beam protected by the thick concrete to avoid the radiation, and those are neutron instruments surrounded the neutron beam. So this is a sample cell I have been working with. So neutron beam can deeply penetrate the cross dart that provide the sample environment and the sample container, and the sample itself directly probe gas molecules inside the pores. So this is the inelastic neutron scattering pattern collected on Tosca instrument. So the experimental procedure is like that. So we seal the clean empty sample cell and insert it into the cross dart, and then pressurize it, fill it with hydrogen, and then we cool down the whole system to 12 Kelvin. And then we know there's a solid hydrogen inside the sample cell because we only pump the hydrogen inside. And then we shine the beam through the cell and collected the data. So this is a typical inelastic neutron scattering pattern. And we see a sharp peak at 14.7 MeV. So that is characteristic peak for solid hydrogen because we only have pure solid hydrogen inside, nothing else. And then we bring temperature up to 17 Kelvin. So then the solid hydrogen melt to liquid phase. The sharp peak disappear becomes not disappear, a broadening, let's say that way. So the sharp peak broadening to a big lump here. And if we continue heat up the system to gaseous hydrogen, and we just get a completely flat curve. So all the peak lump disappeared. So following the similar procedure, we load out the sample inside the sample cell and seal the cell, insert the sample cell in the cross dart and cool down, pressurize it with hydrogen, and then cool down the whole system. But this time, not 12 Kelvin, instead, we cool down the system to 77 Kelvin. And that is much practical pressure, temperature I talk about in a second. So then we shine the beam through, we collected the data. And surprisingly, we see this solid hydrogen peak at 14.7 MeV. So remember, that is characteristic peak for solid hydrogen. But by applying our material, we can achieve this solid like hydrogen at 77 Kelvin rather than 12 Kelvin. Just for your information, 77 Kelvin is liquid nitrogen temperature, and liquid nitrogen temperature is much practical to achieve, affordable. Just for your information, so 1 liter of liquid nitrogen, 77 Kelvin, costs about 1 liter of water. So, without our material, we want to achieve solid hydrogen. We need to cool down to around 12 Kelvin. So that by using liquid helium, and liquid helium is much more expensive. So 1 liter of liquid helium is about 1 liter of fine whiskey. So you see the big difference on price between this solid hydrogen temperature and this liquid nitrogen temperature. Yeah. So by applying the porous materials, we can achieve this very high density solidified hydrogen at much practical conditions. So then we want to know what kind of material will work. Will all the nanoporous materials work for hydrogen densification? And surprisingly, we found not all the materials works, and only the material with a very little tiny small pores with pore size less than 0.7 nanometer can densify solidify hydrogen at this condition. For example, this material is onion-like carbon, which has a much bigger pores, not much bigger, but bigger pore size, larger than 1 nanometer. You can see it from this TEM image, and it doesn't have ability to solidify hydrogen at this condition. So now we know the pore size plays a key role. So how about the pore shape? Does the pore shape also matter? And to answer this question, we selected 3 different porous pore shapes. So they are slit pore shapes, this one, and the cylindrical pore shapes. You can see the cylindrical pores, and the completely disordered structure. And after the massive intensive experiments, and we identify these slit pore shapes can compress hydrogen to the highest hydrogen density. So this is a optimal pore shape. So in industry, in engineering field, we really care about how much hydrogen the material can store in total. So we carried out the high pressure gas absorption measurement. So this is the equipment I have been working with in our lab. So and then this is a high pressure gas absorption curve. We can read the hydrogen uptake. The maximum is about 2.5 weight%. It's not surprisingly high, but what surprised us is the hydrogen density calculated from this measurement. So the hydrogen density for this activity carbon, for example, is 100 kilogram per cubic meter. And that is even higher than solid hydrogen density. And so we really want to know what really happened inside. So we used we carried out the molecular simulation and to visualize us what really happened inside the pores. So this golden sphericals are hydrogen atoms, and the gray sticks are carbon atoms. So we can see hydrogen in this slit pore shapes with a pore size 0.6. Yes? Sorry? Did anybody want to say something? If you have any question, you can leave your question in the chat message box, or we have the questions session later. Can everybody hear me?
I think it might have been a microphone problem.
So can you hear me?
Yes, yeah, we can hear you. You can carry on.
That's fine. So yeah. I just carry on, yeah. So, but if anybody has a problem, just leave the message. Where I am, okay. Yes, molecular simulation. So we can see in this, these are slit pore shapes with a pore size 0.66 nanometer. And in this pore size, pore shape, we can see hydrogen molecules, the golden sphericals, form highly ordered 2 layers. And the space is just too narrow, so hydrogen molecules cannot move around. They are fixed on site. So that's why it's the neutron can scatter with this fixed hydrogen molecules. On the other hand, in cylindrical pores, with a same identical pore size, but the packing of hydrogen molecules are quite different as this one. So the hydrogen form only 1 layer, and hydrogen also got kind of mobility inside the cylindrical pores. So that's the reason why the interaction between hydrogen molecules and the wall of the cylindrical walls are slightly lower than this one. So that's the reason why the hydrogen density inside the single carbon nanotubes slightly lower than the slit pore shapes. So now we know the from this theoretical study, and we identify the optimal pore size that is less than 1 nanometer, ideally 0.7 nanometer, and the pore shape. So based on this investigation, we want to develop a porous composite as a liner to line up the hydrogen storage tank in order to either increase the tank's capacity or reduce its pressure. Therefore, we can use more standard materials and standard regulators so that the tank's cost will be reduced greatly. So we want to, so now we set up our design criteria for the tank liner. So ideal liner materials need to fit that criteria. First, it need to be a good adsorbent for hydrogen. Of course, it need to store hydrogen, and secondly, it need to be able to be processed into membranes. So the material I used in the first study are all in powder form. So powders are very difficult to manage in industry, so it's basically useless. So especially you cannot imagine how to embed the powders inside the hydrogen storage tank. So we want to find the material it can be processed into membrane, and also it need to be strong enough to sustain high pressure and also thermally stable and be able to scale up. And then we found the polymers of intrinsic macroporosity, PIM1, and that is a porous polymer. Polymer is one of the plastic, we can think that way. Maybe it's easier, we are not a polymer person here. So this polymer is invented about 15 years ago by Neil McQueen at UEA, and this material is very interesting. It can be processed into this yellow and transparent membrane, and it's also got a macroporosity, and the pore size is less than 1 nanometer. Tick our box, and it's easy to process into films. However, the hydrogen storage capacity is relatively low, so less than 1%. So this is a good starting point, but adsorptive capabilities need to be improved. So to improve its storage capacity, we doped the PIM1 with porous fillers. So we can see this is a PIM1 granules. It can be dissolved into organic solvent and then cast into transparent yellow film. And those are porous fillers with extra high surface area and hydrogen storage capacities. And the only problem for them, they are powder form. They cannot they are not processable. So the composite membrane combined the good processability with the high hydrogen storage capacity from the fillers. So this we mixed the PIM1 polymer and porous fillers together and dissolve them into a solvent and at a different concentration. And then we pour them into a container, petri dish, and let them dry. And then we just drop a few drops of water on the dried membrane. The water will automatically go underneath of the membrane and lift it up. So that's how we cast the film. So those are the films we manufactured. These are pure PIM1, and these are composite films. And it's a really good thing is we can add quite a lot polymer porous fillers inside. So the maximum concentration is about 60 weight%. But you can see at 60 weight% is already brittle, very difficult to hold its shape. So those are different composite membranes, and so basically with the increase of fillers concentration, the transparency decrease and the flexibility also decreased. So those are top 4 composite membranes. So these are from the cross section of the membranes. We can see how the particles, porous fillers particles, are homogeneously distributed within the matrix, and we can clearly see the boundary, the edge of the porous materials particles. So that means tells us they are physically mixing, so there's no strong interaction between the filler and the matrix. That is good thing, and which is we expected, because that will maintain the surface area and good adsorptive capability. So we fabricated the membrane and then we break them broke them to test their mechanical properties. So this is the mechanical property equipment. Basically, just pull the membrane and then test the force to break it. So the original pure PIM1 membrane is pretty strong. The mechanical property is comparable with carbon fiber. Carbon fiber, that is the material made of the used for hydrogen tank. So the starting point is really good, but as soon as we introduce porous fillers, porous particles, and the mechanical property decreased. And at some point, it will completely lose mechanical property, which means it cannot hold on its shape anymore. So there's a limitation on this. A good thing is all the composite membranes are thermally stable up beyond 200 Celsius in air. That will be good enough for tank. So of course we care about the hydrogen storage capacity. Yeah, that is our aim. So we measured it, the hydrogen uptake. So at 120 bar, 120 atmospheric pressure, the maximum hydrogen uptake is 6%. So continue, if we increase the pressure, and the hydrogen uptake will continually increase as well. But 6% already beyond the DOE target set by Department of Energy. And one of the, so now we achieved our, mostly we achieved our goal. We got the good hydrogen storage capacity, and we can make membrane. And finally, we need to know is a long-term stability of PIM1, because the general problem for polymer is degradation. So the polymer is really easy to degrade, age. So to evaluate its long-term stability, we carried out this 400 days work. So we keep the material and we test its mechanical property and other properties over 400 days. And interestingly, we found those polymer chains are kind of flexible, and they are rearranging and relaxing at the first 15 days. And then stabilize, like fine wine. So the mechanical property shows this feature. So they fluctuated at the first 15 days and then stabilized. But surface area and low pressure hydrogen uptake seems unaffected, which is really good. But the high pressure properties declined slowly, so which is a problem for pure PIM1 film. But then we found introducing porous fillers greatly improve its stability, long-term stability. So we are carrying out this study at the moment, but to be honest, it's nothing changed. So the figure is pretty boring, so I didn't show you here. So introducing porous fillers have a positive impact on aging of the material. So through this 2-year project, and I think we have achieved our research goals. I think, and also the methodology for material design and engineering composites can be applied for other applications. So I think that's also very interesting. Finally, I think we are. What's the next step? We are working towards the commercialization, and I hope the material can be applied for energy storage at a national grid level in the near future, and contribute to a carbon-free hydrogen society, offer our young generation a green future. And also, we need to keep in mind the hydrogen energy is really important to improve UK's national energy security. And finally, I'd like to take this opportunity to acknowledge all my colleagues and friends who contributed to this project and support me for my career development and all the financial support from the founders, and hopefully they will continue to support me to carry out this exciting research projects. And finally, I thank you all for your attention, and I'm happy to take your questions from now.